recording. All right, so we're going over the rules, which describe the types of rules that are necessary to successfully communicate on the network, which is protocols, right? Explain why protocols are necessary in network communication. You should be able to do this. The protocol suites, which TCP/IP and OSI models, standards organizations. These are the organizations that are creating the standards and protocols. You need to know a little bit about each. The different models, again, TCP/IP and OSI. Data encapsulation and data access. I already covered some of this stuff, so I'm just gonna run through it really quickly. Scroll down. Okay, so communication fundamentals. Networks can vary in size and complexity. It is not enough to have a connection device. So you can't just connect a cable and expect everything to work properly, right? The devices must follow communication rules. They must agree on how to communicate, right? You have to have a sender, you have to have a receiver, and you have to decide what type of channel you're gonna be using. So if you're using Wi-Fi, the other device you're communicating with in the local network has to be able to use Wi-Fi too, right? The protocols. Prior to communicating, we first have to agree on how to communicate. Again, if you have to agree on a language and the rules of communication. Next, we need to format the message in a way that's understandable. So everything travels through ones and zeros on the network, right? If you're just sending a stream of ones and zeros, it's gonna be like Morse code, right? There's no way you're gonna understand what's going through there unless you divide those ones and zeros into different groups. So you're gonna say, okay, the first 3 ones and zeros are gonna designate a specific number that tells you what version of IP addresses we're using, whether it's IPv4 or IPv6. After that, there's gonna be another stream of ones and zeros that are gonna tell you what, and this is just an example, what the source IP address is. After that, there's a specific number of ones and zeros that are gonna tell you what destination IP address is, right? So there's rules and standards on how many characters are gonna tell you what information for the devices that are communicating, okay? You don't need to know the specifics, you just need to know how it works. And the analogy says, poor sentence structure can make the message difficult to understand. So if there's not a standard or rules on how to do this, a device is just gonna get a whole bunch of ones and zeros and not gonna know what to do with it. All communications are governed by protocols. Protocols are the rules that communication will follow. These rules will vary depending on the protocol that you're using at the time. Right? If you're face-to-face talking to somebody, you still have to follow rules, all right? And the rules in the networking, they're a lot similar as if you're just talking to somebody. All right, and that's what they're saying here. You have the message source, then the way it's gonna be transmitted. So if we're talking to somebody, you can transmit that information either by voice, by talking to the person, or by writing the information, or showing the symbols, or acting out what the message you're trying to give. There's different ways to transmit the information you're trying to transmit. Transmission medium, that's what that's talking about. The receiver, what signal is that receiver? So as data travels through the network, it might change of how that information is being transmitted. So from one device to another, you could be using electrical impulses. And then from that device to another device, you might be using Wi-Fi radio waves, okay? Each device needs to know how to convert from one signal to another signal, right? There has to be standards and protocols on how to do this, and these devices should know how to do this by default. This is why the standards are created. So right now, most of what we're going over here is why there's standards, why there's protocols, okay? Here's an example of what happens if you don't have standards and you don't have protocols. If you try to read this, you'll notice that it changes languages in the middle of the paragraph. And then some of the information here is not spaced correctly. So it'll be difficult to read it. Same thing with devices. If they don't follow standards or protocols, they'll have difficulty communicating with each other, right? And then you'll see an example of how good grammar is used. Protocols must account for the following requirements to successfully deliver a message that is understood by the receiver. You need an identified sender and receiver, a common language and grammar, speed and timing. If both devices are trying to communicate at the same time, it'll be the same thing as if you and me are trying to communicate at the same time. What's gonna happen? You're gonna start communicating, and I'm gonna start communicating, and then we'll be like, "Hey, I'm sorry, I didn't get what you were saying. I was talking at the same time you were talking," right? So that's where timing comes into play. Speed. Let's say, have you ever read a caption while watching a movie? Imagine if that caption is flying by really, really quickly. Are you gonna be able to read that? Okay, so just a way to visualize that. It has to be a specific, if you're sending information at a specific speed, the device receiving the information needs to be able to read the information at the same speed that you're sending it. You need a confirmation or acknowledgement for the requirements. So again, the devices need to be able to communicate. Are you ready for me to send this information? Yes? Okay, here you go. There has to be conversations between these devices. Network protocol requirements. The protocols that are used in network communication share many of these fundamental traits. In addition to identifying the source and destination, computer network protocols define the details of how a message is transmitted across the network. Common computer protocols include message encoding. I already told you about encoding, right? When you're changing from one signal to another one, or from ones and zeros to electrical impulses, that's what you're using encoding. This is what encoding is. Message formatting and encapsulation, right? Again, ones and zeros. How are those ones and zeros are going to be divided? Each device needs to know, okay, the first ones and zeros I get from a device is a hello message saying, hey, I'm about to send you something. All right. And then you might get an IP address for the source, and then the data that's actually encapsulated in between the source IP address and destination IP address, or something similar to that. Each one of the labels that you're going to add to the envelope being sent through the network is going to have a specific size, and each device needs to know what that size is so that they can read the ones and zeros as they're coming through the interface. All right, the size of the packages. If you send a huge package, then the entire package, let's say 1 gig of information at once through the network, there's going to be problems. So for that reason, it's segmented into different frames or packages or pieces, and each one of those pieces is going to be different sizes, but it has to be in within a range for the size. So it can't be less than a specific size. It can't be more than 15 kilobytes. And it's more, the devices have protocols that say if the packet that arrives on my interface is more than 1500 kilobytes, then drop that packet. It's probably corrupted. And if it's less than, let's say, 100 kilobytes, then it's probably corrupted too. It's probably missing the labels that I need to be able to route the, or to be able to get the information to route this packet. Okay, so timing, size, all those things are important. Okay, here's gonna go over message encoding, and it's gonna give you animation for that. I explained what it is, right? How are you gonna send this message? What method are you gonna use to transmit the information, the signals that you're gonna be sending? Encoding between hosts must be in the appropriate format for the medium, right? Medium, again, is the Ethernet cable or radio waves or light beams, right? Formatting and encapsulation. Again, they're going to give you an analogy of the letter. So there has to be a specific format, how you write the sender address and the destination address, and then where you place that postage stamp. In networking, you're going to have something similar. And throughout the book and throughout the class, you're going to see all these little blocks. These little blocks used to confuse me so much when I was going through the class, right? Don't focus too much on the little blocks, all right? This is representing the information or the labels that are going to go on the message. Just remember that when information is being transmitted through the different cables or through the network, it's being sent in ones and zeros, right? The devices don't actually see these little blocks. These blocks are here for our benefit. It tells us, okay, if on the packet we have a version information or code for the version of the internet protocol you're using, then it's gonna be in either at the beginning or at the end of the ones and zeros that you're sending at one time. And how many bytes of information. So this is important. So let's go to, I like this information. So you go to data size matters. If you type that in Google, it'll take you to an infographic. So if you don't understand what bits and bytes and kilobytes and megabytes are, then this is gonna help you. Again, everything is sent or written onto the computer with ones and zeros. That's the smallest unit of measurement for data, a 1 or a 0, all right? So it can either be a 1 or a 0. If you're doing Morse code, you're using a flashlight, then that light can only be on or off. Think of it that way if you want to, all right? A byte is 8 bits of information. So 8 characters of these ones and zeros, you have 8 bits of information. Each one of those bits can be either a 1 or a 0. And this is how you create the different codes. If you think of it like Morse code, all the information is either ones and zeros, and it's gonna be sent like this, all right? So 8 bits of information is gonna be 1 byte. 1,000 bytes, okay, and 1 byte can be 1 character on the keyboard, or 1 word, or 10 words. I mean, 1 word can be 10 bytes, for example. So whenever you hit a character on the keyboard, like K, for example, the keyboard is gonna send different electrical impulses to the computer or the processor that are gonna be interpreted as ones and zeros. And depending on which ones of those 8 bits that it sends are ones and zeros, is gonna let the computer know, okay, this is the letter K. And if you wanna see what each key on the keyboard is, I believe it's the ASCII keyboard codes. You can look at that. And then it'll give you, you can find online what each code for each letter is, right? And those numbers are gonna be changed from decimal to binary for ones and zeros, all right? Anyway, 1 character is 1 byte. 1 word could be 10 bytes, depending on the size of the word. 1,000 bytes make up a kilobyte. 1 kilobyte can be a short paragraph, or it can be a written page, or it could be 2 kilobytes, right? 100 kilobytes can be a low resolution photograph. So this is just gonna give you an idea of how the size of data, how it works, okay? So I'm gonna go back now. All right, so that's what this means over here, byte 1. So I'll tell you, this packet right here is gonna be sending 40 bytes of information, right? At the beginning of this message, or at the end, right? So the first ones and zeros that you send is gonna be half a byte, so 4 bits of information. And it's gonna be a code that is gonna tell the device what version you're using for the IP protocol. What traffic class are you sending? What type of information you're sending? And again, we're not gonna go into each one and what it is for each one. But then you're gonna have a flow label, and it'll tell you how many bytes of information that's gonna be. So everything is grouped in ones and zeros. There's ones and zeros. The devices need to know what the first ones they're receiving are gonna mean, and what the ending ones are gonna know, and where each bit of information ends, so it knows what the new information is gonna start. So where the version bits end, that's where the traffic class starts. And then the flow label starts. And then the payload, this is where your actual data that you're sending is gonna be, all right? The rest of the stuff is stuff that's encapsulating this payload. Everything's being things that you're adding to your data, so it's able to be routed through the network, okay? Then you have a next header information, and then hop limit. And then you'll have your source IP address and destination IP address. This might be at the end or at the beginning. This is all information that needs to be placed on your frame or packet for it to be routable on the internet or on the network. Okay. Again, this is just for you to be able to visualize this information, and you'll be seeing a lot more of this later on through the chapters. You don't need to memorize the specifics. So don't focus on this. Don't get confused if you feel like this too much. It is too much. All right. Message size. Here's a quick analogy. When people communicate with each other, the messages that they send are usually broken into smaller parts or sentences. These sentences are limited in size to what the receiving person can process at one time. It also makes it easier for the receiver to read and comprehend. And here is a little animation of that, right? If it actually shows anything. Here you go. If it sends everything all together, right? The entire message, no pauses whatsoever, it's going to be difficult to understand. If you break it down like they did here, now you can understand it. Same thing when information is traveling through the network. You have to break down the data into different pieces and then send them one at a time, just like that. All right, moving on. Message timing. Managing timing includes the following: flow control, response timeout, and access method. Let me go to that in the PowerPoint so I don't have to read the entire thing. Flow control manages the rate of data transmission and defines how much information can be sent and the speed at which it can be delivered. All right, and again, these devices, if they're communicating directly to each other, they have to have this flow control. It has to be the same on both. So one device is not sending information faster than the other device can read it. Response timeout, right? So if I'm talking to you and I ask you a question, right, I'm gonna wait 20 seconds. If I don't get information or an answer back to you in 20 seconds, then I'm going to assume that you're no longer in the Zoom meeting. You're not there, so I'm gonna stop asking you questions. Same thing with these devices. If one device is gonna communicate with the other one, the first thing it's gonna do is try to get a reply from the other device. If the other device doesn't reply in a specific amount of time, then this device is gonna assume that the other device is not on the network anymore, okay? Response timeout manages how long a device waits when it does not hear a reply from the destination. Access method determines when someone can send a message. So if the devices are both sending data at the same time, the communication is gonna collide. So they won't be able to communicate. There's gonna be, the data is gonna get corrupted, okay? Access method determines when someone can send a message. There may be various rules, various protocols governing issues like collisions. This is when more than one device sends traffic at the same time and a message becomes corrupt. Some protocols are proactive and attempt to prevent a collision. Others are reactive and establish a recovery method after collision. So some will try to prevent it. Other ones are gonna be like, okay, if there's a collision, I must send the information again. And you can find out, you can read more, is more detail here if you want to read it, right? And here's an animation on that. What time is the movie? And then they're both talking at the same time and they can't understand each other. All right, good, moving on. Message delivery options. All right, so when you're talking on a forum or on a chat message, for example, you can send a broadcast. Everybody should know what a broadcast is, right? You're sending a message to everybody on the chat group, right? That's an example of a broadcast. So these devices can do the same thing. They can send a message to other devices on the local network and send a broadcast as a broadcast. So there's one package that the computer is sending will get to the switch, and then the switch is gonna send that packet through every interface on the switch so that all the devices connected to the switch will get the message. This is a broadcast. Then you have multicast. This is when you're sending a message to a specific group of people. So if everybody in the chat, maybe I pick 3 people that I'm gonna send a message to, and only those 3 people are gonna get it. That is multicast. Unicast is when you're talking to only one person, specifically one device on the network. That's unicast. Just have an idea of what each one of those is. A note about nodes. So you might see symbols like this ones to be able to reference, like for example, here you'll be able to see. So the nodes, networking documents and topologies often represent networking and end devices using a node icon like this one, the circles. Nodes are typically represented as circles, right? So here they're using it to be able to give you an example: broadcast, multicast, and unicast. The green nodes are the ones receiving the message. All right, so you can do this activity on your own. Moving on. Protocols, overview on protocols. All right, so network protocols define a common set of rules. They can be implemented in devices in either software. So these rules can be set up on the software, on the hardware, or on both. All right, so it can be embedded on the hardware, or it'll be something that you configure, or it can be an operating system as default configurations. Protocols have their own function, format, and rules. All right, so network communication protocols. These protocols enable 2 or more devices to communicate over 1 or more networks. All right, and some examples of these protocols are the TCP protocol and the hypertext transfer protocol. I told you TCP protocol is used whenever you want reliable communication. HTTP is used for website data, right? Whenever you go to a website, you might notice something like HTTPS or HTTP. That will tell you what protocol is being used at the application layer. This is what's giving the service to the web server to communicate on the internet. If it's HTTP, this is going to be not encrypted. Information is going to go as plain text through the network. If it's HTTPS, then they're going to be using SSL or TLS, a service on the presentation layer that's going to encrypt the information if you're using SSL or TLS. Yes. And I believe it's the presentation layer that's going to do this. Okay. Network security protocols. Protocols secure data to provide authentication, data integrity, and data encryption. Examples are SSH, when you're using SSH to communicate with a device on the network, secure socket layer, SSL, or transport TLS, transport layer security. That's what that stands for, okay? It's just talking about the different types of protocols you might find. Routing protocols. Protocols that enable routers to exchange route information, compare path information, and then select the best path to the destination network. So the routers know about these different protocols, and you might configure these different protocols. Depending on what protocol you're using, the routers are going to follow different rules to find the best path. Remember that you might be, if you're on the internet, there's multiple routers that can connect you to one a network remotely, right? So there's different paths that the information can take. One of the jobs of the routers is to find the best path, okay? And so you'll be using OSPF as an example of one of the routing protocols that you might use to automatically find the best path. Another one is Border Gateway Protocol. Service discovery. These protocols are used for automatic detection of devices or services on the network. So examples of this are going to be the DNS and the ACP. The ACP gives out IP addresses automatically to devices on the network. DNS will have a list of IP addresses for websites and the website names. So that way you don't have to memorize the IP address for each website. You just memorize the name for the website, like google.com, instead of the actual IP address that you would type in. Again, all you need to know is different types of protocols. You don't need to learn the specifics yet. Just remember that there's different types. Don't focus on the details or you'll get confused because there's too many of them. Network protocol functions. Network communication protocols are responsible for a variety of functions necessary for network communications between devices. For example, in the figure, how does the computer send messages across several network devices to the server? So again, one of the information that you're gonna add to your data, you're gonna encapsulate on the layer 3 is gonna be this IP address, the source IP address and the destination IP address. You have to decide, are you gonna be sending the information through IPv4 or IPv6? Right? Before you send the message. When it arrives to the device, it has to look at the information. Am I capable to send this information in an IPv4 network? If not, do I have IPv6 configured on the device? All right, moving on. Computers and networking devices use agreed upon protocols to communicate. These are some of the different type of protocols. Addressing protocols. This identifies the sender and intended receiver. IPv4, IPv6, for example. Reliability. This function provides guaranteed delivery. This is an example again is TCP. All right. So UDP is not reliable, TCP is reliable. If you want to remember that, that's cool. Flow control. This function ensures that data flows at an efficient rate between two communication devices. TCP provides flow control, which there's a communication going out throughout the entire process of communicating and sending data between the devices. Sequencing is when you divide that one packet into different segments, and then you number each one of the segments so that whenever each segment arrives to the destination device can put all those segments back together and give you your output, your final product. This function uniquely labels each transmitted segment of the data. The receiving device uses the sequencing information to reassemble the information correctly. Error detection. If there's a problem or the data is corrupted, the devices need to know this, right? So they can try to fix it before the data is compiled back together and the destination device. Application interface. This function contains information used for process-to-process communications between network applications. For example, when accessing a web page, HTTP or HTTPS protocols are used to communicate between the client and the server web process. All right. So this HTTP and HTTPS are going to provide services to the web browser to be able to communicate through the network. Again, just an overview. You can go over each one again, but just remember that there's different protocols and standards throughout the entire communication process. Protocol interaction. So you have different protocols for different, each protocol has a different job, but these protocols might work together for a specific job. For example, if you have HTTP for a web browser, right, or a web site, when communicating through the network, you can use SSL or TLS to encrypt that data. TLS is found on a different layer on the OSI layer, on the OSI model or TCP/IP model, but they're both working together to send information and encrypt information at the same time. Right? This is what this slide is talking about. The different layers will have protocols that interact with each other to be able to work and complete a task. Some of the protocols that you need to know about are hypertext protocol, HTTP. It'll give you a little bit of information about that. Oh, this is skipping through it. All right. Transmission control, TCP. I already explained a little bit about it. I'm not going to do it again. Internet protocol. This protocol is responsible for delivering messages, IP addresses, source IP address, and destination IP address. Ethernet protocol. This is the protocol responsible for the delivery of messages from one network card, the actual physical card on the device where you connect the cable, or the one that has the antenna to send radio waves, right? From one network card to another network card. All right, moving on. And you can go through this on your own. Network protocol suites. This is where they introduce you to the OSI model and TCP/IP model. And again, think of them like a way to group all the different protocols into different layers so you can better understand them. This is talking about how we started with OSI model, and then we moved on to the TCP/IP model is what is being used. The TCP/IP model has 4 different layers: application, transport, and internet and network access. Those are going to relate to the different layers on the OSI model. We'll go over those in a little bit. Internet protocol suite, or TCP/IP, is the most common and irrelevant protocol suite used today. Right? It's maintained by the Internet Engineering Task Force. There's an organization that maintains all the different standards and protocols in this model. Open System Interconnection Protocols. This is the group of protocols that started everything, okay? The OSI reference model categorizes the functions of its protocols. Today, OSI is mainly known for its layered model and is really used just to teach the concept itself. And both of those are open source, meaning that anybody has access to them. AppleTalk is a model that was created for Apple and is proprietary. Novel Netware is another proprietary protocol suite. Moving on. TCP protocol examples. Protocols that are found on each layer. And again, HTTP, TCP, IP, and Ethernet. We're going to go over this stuff over and over again until you memorize it. All right. Here's examples of different protocols that you might find in the different layers. Application layer, remember, the protocols on this layer give services to the applications that need access to the network, right? So you have DNS protocol, you have DHCP, DHCP version 4, DHCP version 6. Slack does the same thing as DHCP, but for routers. Email, whenever you're sending an email, when you're sending emails, you're gonna have different protocols. For either sending the email, you might be using SMTP. You're gonna be using SMTP to send the email. To receive email from a server, you might be using POP3 or IMAP. If you're transferring data through the network, you might be using FTP, SFTP, or TFTP. We're gonna use TFTP to transfer the configuration file from the router or switch to the computer to be able to back it up or store it. The web services are gonna use HTTPS, HTTP, or REST from the application layer. These protocols are found on the application layer. Transport layer is gonna use TCP and UDP. Those are examples of the protocols you might find there. Again, one is connection oriented and more reliable. The other one is not reliable. It just sends the information as long as it has a destination IP address, starts sending all the data as quickly as possible. UDP is faster, TCP is slower because there's more communication going on there. Internet layer. On this layer, you might find IPv4 protocols, IPv6, NAT. We'll go over these protocols later on, what they mean and what they are. Messaging, if you're trying to check that you have connectivity with another device, you will send a ping, right? An ICMP package. ICMP version 4 for IPv4 networks, ICMP version 6 for IPv6 networks. If you're configuring a router to communicate or find the best path on the network, you might be configuring OSPF using OSPF protocol or EIGRP or BGP. Again, don't focus on the specifics, just have an idea of what protocols are found on each one of the layers. So again, if you're feeling confused with everything we're covering right now, you just need to know about it. You need to be presented to it so that when we go later on in the chapters, you find it again, be like, okay, I remember a little bit about it, all right? You have something to stand on, something to base or to base from the rest of the information that you're gonna get. TCP/IP is the protocol suite used by the internet and the networks of today. TCP/IP has two important aspects for vendors: open standard protocol suites, meaning that anybody can use the standards and protocols, right? Freely available to the public. Standards-based protocol suites. The rules are based on standards, so everybody should follow the same rules. So everything should work together the same way. Application layer, transport layer. He's gonna go more in depth on what each protocol does. You should review this information, right? DNS domain name system translates domain names such as cisco.com into IP addresses. They use this server, this protocol, so that you don't have to memorize each IP address for each website out there. Google and Facebook, every single one of them is gonna have their own IP address. And I'll give you an example. If I do a ping google.com, this computer will receive a reply from google.com. It'll give you the actual IP address for the device, or for the server, I mean. All right? Before, if you didn't have DNS, you would have to memorize each one of the IP addresses for all the websites out there. So a DNS has a library of IP addresses or website, the names of the websites, and the IP addresses that are attached to those websites. All right? And then you can read more information about each one of the other protocols on here. Important, you will be seeing these protocols again. Is going to be good that you know about them. Okay? You have TCP/IP. Everything that we've gone over is going to give you an explanation of what it is. All right, moving on. TCP/IP communication process. And here's going to tell you how data gets encapsulated. So if you remember the analogy I gave you, you start with your letter that you're sending. That gets placed in an envelope. That envelope is going to have different data pasted on it, labels that you're going to put on there. Then it's going to go to the next layer, which is going to be placed on a new envelope. And that envelope is going to have labels specifically to that layer. That's what he's talking about here. So if you go over this, you get confused, try to remember that analogy. Then the animation and figure demonstrates the complete communication process. So let's look at that animation real quick. There's my website. That's the data I'm trying to send. It gets placed on the envelope for the data. That data is going to be sent to the next layer, and it's going to have information added to it, right? Then it goes to the next layer, and more information gets added, like the source IP address and destination IP address. Then it goes to the next layer, and more information gets added to it. And then it gets sent through the cable, right? That's ones and zeros. Each device needs to know how those ones and zeros are separated. The first 3 ones and zeros are going to mean something. The next 10 are going to mean something different. The next 20 are going to mean something different. This is how the devices know how to read these ones and zeros. And then when the data is received by another device, it follows the same thing, just in reverse. So it gets received by the physical layer, then it goes to the internet layer, and then it moves on to the other layers until it gets to the application layer. And as it goes through the different layers, each layer is going to remove the labels that it needs and then send it up to the layer above. And the layer above is going to remove the labels, is going to read the information that is on the labels that it requires, then it's going to discard those labels, and whatever's left is going to send it to the layers above until it gets to the application layer, and all you're left is with the data, and then it outputs the data to the user. All right, moving on. Now you have information about the different organizations that create the standards and manage the different standards. You should go over this information. You might get questions about these organizations on the certification. All right, so you have Internet Society, responsible for promoting the open development and evolution of internet use throughout the world. Internet Architecture Board, responsible for the overall management and development of the internet standards. You should know what standards are. Again, think of them like blueprints and templates on how these rules should work. Internet Engineering Task Force develops, updates, and maintains internet and TCP/IP technologies. This includes the process of and documents for developing new protocols and updating existing protocols, which are known as requests for comments RFC documents. Internet Research Task Force focused on long-term research related to the internet and TCP/IP protocols. Moving on. You might get questions about IANA and ICANN. So if you don't remember the other ones, try to remember this too. And also IEEE. All right. This one right here, based on in the United States, coordinates IP address allocation. These are the guys that decide what group of IP addresses each ISP is going to have. Okay. Remember that the IP addresses are divided into different groups. And then these groups are assigned to specific organizations. You can't just go and use whatever IP address you want because there's not enough IP addresses for everybody. IANA responsible for overseeing the managing IP address allocation. So they oversee what ICANN is doing. They oversee and manage whatever ICANN. They work together. Then you have IEEE. They're in charge of networking standards for the devices, right? And in charge of other stuff. But for us, what's important is telecommunications and networking. EIA is in charge of connectors, the connections, different connectors that you use to connect these devices and the network equipment. Whatever standards and protocols that are used to build these technologies. Industry Association, TIA, they create the standards and protocols for cellular towers, voice over IP, satellite communications, and more. International Telecommunications Union, Telecommunication Standardization Sector, ITUT, one of the largest. This one's in charge of the different broadband technologies like DSL, which is one form of communication that is used by the ISPs, right? DSL, cable networking, IPTV, things like that. All right, we can move on. We have three more sections. Benefits of using layered model, assisting in protocol design because protocols that operate at a specific layer have defined information. So whenever you're creating these protocols and standards, you can focus just a specific group of protocols. You don't have to think about all the other layers, just one specific layer. Fostering competition, again, analogy, if you're creating a USB cable, then there's a specific standard or blueprint on how to build it, so anybody can go and build one. And this will foster competition because there'll be different prices and you'll be able to buy from any manufacturer, and the cable should work exactly the same, preventing technology or changes from affecting other devices. So if you follow the standard on this USB cable, right, you won't have to change how the device is going to use it. So, or the hardware on the device that's going to use it. The hardware on the device that has a USB port should be able to use whatever USB cable you connect to it, providing a common language to describe networking functions. So when you're learning about networking, it's easier to have all these different layers or these different standards and protocols and different groups, so you can break it down and then learn about it like that. All right, here is a reference that connects the two OSI model and TCP IP model. We went already through application presentation session in each one of these layers here. The first 3 layers on the top, the application layer on the TCP IP model does the same jobs that those on the OSI model, the same jobs they do, right? So if you have HTTP on application layer and DNS, the application layer on TCP IP model is gonna do that, but it's also gonna do the presentation, which includes encryption, compression, and formats, different formats that are gonna be using. It's also gonna do the same job as the session layer. The transport layer and the transport layer TCP IP model and the OSI model are gonna do the exact same thing. The networking layer is gonna do the same thing as the internet layer and the TCP IP model. The data link layer and the physical layer, again, this is gonna do the same thing as the network access layer and TCP IP address model. And I kind of broke down each job for each layer on the other video. So go back to that one if you want to go over this again. But if you look at the different chapters, you'll see that each chapter has a different layer that is going to break down. The OSI reference model, and this information that I already gave you, so I'm going to skip it. It's going to tell you what each layer does or the jobs for each layer. You should go and read the more details on it if you want to learn more about it. And then same thing. So let's go over this one. Application layer for the TCP IP model represents the data to the user, plus encoding and dialog control. I don't know if that's gonna make sense to you, but again, it's gotta do with how the application communicates with the network. The service is used for that.
I had to drop off. Thanks for class, okay?
All right.
I gotta go.
You can watch this video later. Transport layer. And again, this is going to get broken down in the next chapters. Supports communication between various devices across diverse networks, right? And remember that in here, you're going to find TCP and UDP. The internet layer determines the best path through a network. That's where you're going to have your IP addresses and the routing protocols. Network access layer, this controls all the hardware, the actual physical part of the network, your cables, your network cards, your routers and switches. All right, moving on. Same thing here. We're going over the same stuff that I already covered. You can go here and read the details for that. Can move on to encapsulation. Again, I try to help you visualize this with the analogy of the envelopes, where you're adding an envelope, you're adding labels to that, moving into the next layer, into a new envelope with new information added to it. Knowing the OSI reference model and the TCP IP protocol model will come in handy when you learn about how data is encapsulated as it moves across the network. I explained this on the other video. I'm just gonna move on from here to the next slide. This leads to segmenting messages having 2 primary benefits. Okay, so you're segmenting the different jobs in the communication process. This will help increase the speed, because a large data stream is segmented into packets, and we're talking here about segmentation. This is the transport layer. A large amount of data can be sent over the network without tying up communication links. This allows many different conversations to be interleaved. So, and let's talk about this. Multiplexing is what it's talking about. So when you're sending data through a network, look at this animation. You break down the different data, right, into different pieces. If you were gonna send the data in one piece, then only one device can communicate at a time, is what it's trying to say. But if you divide all the data into different pieces and you give a number to the different pieces, then it doesn't matter how you send the data. You can send the different pieces mixed with information from another computer. But because everything is properly labeled and has different numbers for the different segments, when it arrives to the device, that other device can put all the different pieces together with the information that you labeled on the device. And so you can send information first, one packet from one computer, and then another packet from another computer, and then the next packet, and so on. It can interweave the information being sent. This is known as multiplexing. This increases efficiency. If a single segment fails to reach its destination due to failure in the network, this device can send that one segment only to the device receiving it, instead of sending all the communication all over again, all the data all over again. Just that one file that didn't arrive. Sequencing, again, here's an example of that, where every packet is labeled, and then it doesn't have to be sent all the packets for this device only first, and then this device. No, everything can be interleaved and sent to the other. Hopefully you understand what we're talking about here. So sequencing. If you don't understand, please ask me on the next meeting. And I think there's 2 of you here. If you have a question about this, ask me right now. Hopefully this makes sense to you. We're talking about sequencing and multiplexing. All right, and segmenting. Okay, so far so good, good. Moving on. Again, I tried to speak about this before so that you understand that as we're going through here. Protocol data unit. Okay, so every one of this packets, so the data, when you have your email and you break it down into different pieces, right? Different segments, and it's traveling through the different layers, this data, each one of these packets, they're known as protocol data units, okay? As you go through the different layers, these protocol data units might have a different name, like a frame or packet or bits of information. If you're in the physical layer, sending information through the physical layer, the data is gonna be known as bits, ones and zeros, okay? Just know that PDU, if you ever see a PDU anywhere on this book, on the course, it's talking about the datagrams that are being sent through the different segments that are being sent through the network, right? So application data is passed down through the protocol stacks on its way to be transmitted across the network media. Various protocol information is added to each level. Remember the labels I was talking about. Although the UDP, right, or PDU is called the datagram. Huh, what? PDU is called the datagram. IP packets are sometimes also referred to as IP datagrams. All right, so different names you're gonna find for the different data as it travels, right? So you might find segments, packets, frames, or bits, depending on what layer you're in, right? And you're gonna get information added to each one of these packets that has your main data on it, right? We went over this. And then at the end, it's gonna travel as signals that represent ones and zeros. Right, so data, the general term for PDUs used in the application layer. So if you're in the application layer, these packets are gonna be known as data. If you're in the transport layer, the packets that are traveling through there are gonna be known as segments. This is where you segment the information into different pieces. If you're in the network layer, these are known as packets. If you're in the data link layer, these are known as frames. If you're in the physical layer, these are known as bits. Remember the ones and zeros. You need to know these terms because you're gonna see them again throughout the chapters. Encapsulation example. Here's an example. I've given you my own examples, and we're just gonna go through the animation already. I mean, just gonna go through the animation. I'm not gonna explain it again. Just showing you how data is added to it. We've seen this animation. Moving on. De-encapsulation. That's talking about when a device sends the information, it encapsulates all the data, right? With different information, it adds information to it. When the information is received on the other device, is going to de-encapsulate the data. It's gonna remove the information at each layer that requires the information and end with just the data that it needs to transmit at the application layer. All right, good, moving on. And it looks like I might finish before 10 p.m., which is good. All right, this is something we haven't covered, data access. So let me stop this video and have a separate video for this.